All right, so the last intermolecular force we're going to look at is London dispersion forces. Okay, so we're going to first kind of understand. So we'll we'll talk about who can do it and then how they work. So the first is that all molecules can have London dispersion forces. So this is again LDFs. So every molecule, no matter it is not the most dominant interaction. So for most molecules, unless it's the only interaction you can have. So only intermolecular force (IMF) for nonpolar molecules. For nonpolar molecules. So often LDFs are associated with nonpolar molecules for this reason, because it is the only interaction, but they do impact properties, especially for larger molecules. So there are two important factors to understanding the strength, and once we know these factors, we'll talk about how it works. So two important factors affecting the strength of LDFs. So the first we look at is something called polarizability. Okay, and this is a measure of how easy it is to distort the electron cloud surrounding a molecule. Okay, so this directly has to do with Z effective. You can move so electrons that are further out from the nucleus have a higher polarizability. So we can say that larger molecules are generally more polarizable. So the first thing we look at is how large molecules are, and by large we can look at number of electrons. So just look at the atomic number, and we have an idea of its polarizability. The larger the molecule, the more electrons. It means that you're going to have more core electrons, the effective will be lower, and you'll be more polarizable. Now, for molecules that have the same number of electrons, or are the same size or roughly the same size, then we have to look at this distance dependence for the interaction. Remember that we have this interaction is proportional to 1 over r to the 6th. That is extremely close. That distance dependence drops off dramatically because of that the 6 power relationship. So LDFs, so shape is the other one. So shape of molecules, shapes where we can maximize overlap, maximize context area are going to be stronger LDFs. So LDFs occur only at very short distances. So shapes that have so more surface area for interactions between molecules will result in more dispersion forces. So we're going to see both of these, both shape and polarizability, and a couple of trends. So I'm going to give you those. So The first trend I'm going to give you is just size. So if we look at size first, we can see that, so I'm just going to do a bunch of hydrocarbons. These are all nonpolar. So I'm just going to add in a CH2 group to the first molecule, 3 carbons, and then another CH2 group. So we're just making this bigger by a CH2 group. And we can see that the boiling point, which again is a very good indication of the strength of the intermolecular forces, not just for London dispersion forces, but for all strength of forces. Melting point is for ionic compounds because they tend not to be a liquid at room temperature. So this is negative 88 degrees Celsius. We already have that. And then it goes up, so it becomes smaller negative value to negative 42, and then negative 0.5. Okay, so that's so there's 2 reasons. This is larger, but also we're getting big enough to have more surface area for LDFs. So, and we'll show that in a sec. So if we can look at how shape factors in besides size. So let's look at, so we can have a carbon, 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 carbon. And if we draw this out, this is this molecule. But the reason I'm doing that is I'm actually kind of showing a better representation of a 3-dimensional molecule. And we can draw this in line structure, which is we just connect the carbons together. So we can represent this structure using a line structure. Okay, so now that we know that, then we can look at and say, well, we have 2 molecules. One is this molecule, which is has a boiling point of negative 0.5. We just said that. And then if we look at this molecule, which is basically the same 4 carbons. So both of these have the same number. So these are the same size. The boiling point here is negative 11.7 degrees Celsius. So again, not as big of a difference as we saw from like going from like changing in size. But we can see that the difference here is shape. So for the top molecule, we can stack these molecules on top of one another and pretty much have interaction surface area over the course of the whole molecule. But for the branched version of this molecule, we can only get about 1/3 of the interaction space. And so because of that, we tend to see, so let me just highlight this. So the interaction space is along the whole length of this molecule, where it's only 1/3 of this molecule. So we see this reduction in the places in which we can have an interaction. That reduces the number of interactions that can occur. Okay, and this is actually what we see for saturated and unsaturated fats as well. So if you ever wonder why saturated fats were always assumed to be bad and unsaturated fats were better, it's because of this same principle. So we have a fatty acid head group that's polar, but then fats are known for having their long hydrocarbon tails. Okay, this is a saturated fat. Saturated just means that it doesn't have any double bonds, and it has a melting point of 63 degrees Celsius. Okay. And then if we take a unsaturated fat, same polar head group, but then we're going to have at some point a kink where we have a double bond. It's unsaturated. So if we have the same number of carbons and hydrogens, so it's the same mass, this is a unsaturated fat. Its melting point is 4 degrees Celsius. Okay. So it's and so actually unsaturated fat a lot of times are oils. Fats and oils are only different by what their physical state is at room temperature. Fats are solid at room temperature. Oils are Liquids are room temperatures. So we would technically say that this unsaturated fat would actually be an oil. But this kink here, so what's happening is this kink caused by the double bond reduces number of LDFs based on shape of molecule and how they can stack and overlap. So this is a very a nice way to show how both size and shape play a role in London dispersion forces, though these are not the greatest by magnitude per interaction. You can have many more LDFs occurring over a length of larger molecules, and so they can actually be more impactful to physical properties than boiling points, such as boiling points, when you have the potential for other interactions like dipole-dipole. So for things that aren't nonpolar, LDFs can actually be the dominant interaction. Again, we won't get to that, we won't show that, but we'll definitely see that in second semester general chemistry.